Hi all, my name is Konstantin Yakovlev and this is joint work with Anton Andreychuk and Roni on bounded-suboptimal safe interval path planning. So in this work we are motivated by a challenging problem of finding a safe path for an agent in the presence of dynamic obstacles, and often from practical point of view we are interested in getting suboptimal solutions fast rather than investing extra computational budget in getting probably optimal solutions. So we frame this problem as graph search, and the vertices of the graph represent the locations in the environment an agent can occupy, and the edges represent the transitions between the locations, and due to the dynamic obstacles certain graph vertices are blocked for certain time ranges, and the same applied to the edges. And in this scenario the solution is not just a path in this graph, but rather a plan, which is a sequence of actions, and each action is either move or wait, where move is naturally moving from one vertex to the other, and wait represents staying in the same vertex for some amount of time. So the duration of an action is its cost, and the sum of actions durations defines the cost of the plan. And in this work we're interested in getting bounded suboptimal plans, which are defined as in the bottom of the slide, where W is the suboptimality factor, which is set by the user. So SIP, safe interval path planning, is a powerful algorithm tailored to solve this kind of search problems, and the core notion of SIP is the notion of safe interval. Formally, it's a continuous period of time during which the vertex is not in collision with a dynamic obstacle, so it's safe to occupy vertex within a safe interval, and it's not safe to occupy the vertex otherwise. So SIP uses the notion of safe interval to define the search nodes. So the search node is a tuple, graph vertex, and safe interval. Obviously, when we define this search node in such a way, we allow having different search nodes referent to the same vertex, but having different safe intervals as on the picture. And basically SIP runs a star in this search space, and it relies on admissible and consistent heuristics, and when it explores the search space and expands a node, it tries to achieve each successor as early as possible. And this strategy, backed up with consistent heuristic, guarantees that SIP is complete and optimal. Recall, however, that in this work we are interested in bounded suboptimal solutions, and we explore two different ways how to achieve this. The one is using the inflated heuristics, is when we multiply the given consistent heuristics by the suboptimality factor, and another one is utilizing the focal search framework. So regarding inflated heuristics, so in general it's proven that in SIP we cannot prohibit re-expansions. So the first algorithm that we try, which we explore, is WSIP-R, is basically SIP which uses weighted heuristics and allows re-expansions. No limits on re-expansions are imposed. Another algorithm which we explored was the one introduced in the paper by Roni and et al. The idea of this one is to limit the number of expansions in the following sense. So when a node is expanded and successor generated, we basically create two duplicates of this node which differ in their f values and insert both of them to open. This was proven that when we do it like this, we can prohibit re-expansions. So each of the copy of the node is expanded at most once, and we guarantee that we are bounded suboptimal in the end. So focal SIP is a straightforward application of focal search framework. This is when we identify a subset of open nodes and call them focal. So we do it in the following fashion, that the g value plus h value is less or equal than suboptimality factor multiply minimum f value in open. And if we do it like this, then we can use an actual heuristic function that doesn't have to be consistent or even admissible for choosing the nodes from focal, and we still guarantee that we will end up with a bounded suboptimal solution. So the intuition here is that we're using some informative heuristic which rapidly progresses us towards the goal. So which algorithm to choose is the core question. It's actually like an open question. Consider, which is not that straightforward to answer. Consider, for example, the choice between W-SIB-D and W-SIB-R. It might seem that avoiding re-expansions is always good. However, when W is low, we have those two duplicates in W-SIB-D, and when W is low, their F values are really close to each other, and it's likely that they both will be expanded. So technically we can count this is one re-expansions, and maybe W-SIB-R will not do those re-expansions at all. So this is a hypothesis one need to test. If W is large and we have an informative heuristic, secondary heuristic, then probably focal SIP is our algorithm of choice, because it just rapidly goes towards the goal, and that's it. So to validate these hypotheses, to test them, we conducted a thorough experimental evaluation that involved different maps, which are grid maps with different connectivity levels. We allowed and disallowed rotations, so in some settings rotation took time. We override the suboptimality factor, and basically the results that we get were all consistent across all the setups. So here I will talk about just two most representative setups: the warehouse, which represent like an open environment with isolated obstacles, and in this setup Euclidean distance, which we use this heuristic, is a relatively accurate heuristic, and rooms, which represent an indoor environment with narrow passages, and here Euclidean distance is much less accurate heuristic. So the first thing I want to talk about is that indeed when suboptimality factor is low, using W-SIB-R is better than W-SIB-D. It's what we hypothesized before, and this is proven to be true by the experiments. Another thing which is interesting is this notable spike in the mid-range of W for focal SIP. So we hypothesize that this is due to the fact that focal SIP starts progressing fast towards the goal. However, due to the constraints on the suboptimality, at some moment of search, it has to go back and re-expand the nodes in the close to the root of the search tree. So focal SIP is indeed good when W is high, as expected, but not in the mid-range. In the mid-range, W-SIB-D is a ultimate algorithm. So the plot on the left that shows the number of re-expansions also confirms those two claims, and on the right you see the scatter plot of runtime versus suboptimality. So basically, if we look closer to it, what we see that if we want to get the solutions fast and we don't care that much about the cost, then we use focal SIP. If we want to get really close to the optimal solutions and we do not mind spending extra time on this, then W-SIB-R is a good thing. So in all other cases, then W-SIB-D is a good thing to try. So to wrap up, in this work we explored 3 different versions of bounded suboptimal SIP, and we conducted a thorough experimental evaluation that showed that there is no universal winner. Still, we have provided guidelines when to use each algorithm, and obviously the prominent direction for future research is creating more involved bounded suboptimal SIP versions by utilizing more advanced search techniques that make heuristic search suboptimal, bounded suboptimal, and we can also try to construct an enhanced anytime SIP as well. So thank you very much for your attention. I'll be happy to answer your questions.